Ya, Assalamualaikum warahmatullahi wabarakatuh. Good morning, noon, afternoon, night, all. So, in this week, we will learn about the mathematical analysis of a recursive algorithm again. Last week, we learned about homogeneous characteristic equation. So it is how to solve a recurrence relation by using homogeneous characteristic equation, where we have the recurrence relation in the form of a 0 Tn plus A1 Tn minus 1, and so on until An equals to 0. So this is recurrence relation, linear recurrence relation, and this part make it homogeneous. And today we will learn about the case where this part is not 0, which is non-homogeneous. Okay, so this is the type of the form of non-homogeneous linear recurrence relation. Sorry, it's supposed to be relation. So in this case, Fn is in the form of Bn Pn. Okay, so it is B to n, and we have some polynomial. And we may have more than one form of this. So we called it as a term. And in this part, we may have more than one term. So for example, we have 2n times n. It is in the form of this, but we may have it added with something else. For example, 3 to n, like this. So we have two terms, this term and this term. It is still a non-homogeneous linear recurrence relation. Okay, so we have another theorem here where suppose there is a homogeneous linear recurrence relation with constant coefficient. I'm sorry again, it's supposed to be non-homogeneous. So we have this. Then the characteristic equation will be this part will be exactly the same as the homogeneous part we learned last week. But now we have additional characteristic equation, so it will be multiplied by this. So this is R minus B based on this, okay, and then D. D is the degree of the polynomial. And if you have more than one term, for example, here you have B2 and the second polynomial, then you will need to multiply it again by the second term. Like this, okay? So polynomial degree is the highest degree you have in the polynomial. So for example, in this polynomial, the highest degree is 2, so 2 is the degree of the polynomial. And in this case, the degree is 1. And in this case, actually, it is multiplied by n to 0, right? So the degree is 0. And then, like what I said before, the part, the right-hand part of the equation will be in this form. So if you have this linear equation, then in this part, you can see it is B to n. So B will be 4. And the polynomial for n is actually 4n times 1, right? Where this is the polynomial uh, of degree 0. So Pn is equal to 1. So the degree will be 0. And K is the highest abstraction we have in the index of T, where the highest abstraction we have here is 1. So in this case, k is 2, and in this case, k is 1. And from here, you know that b will be equal to 4, and this is the polynomial part. And we know that the degree is 1. And from here, we know that 5n plus 7, we can write it as 1 to n times 5n plus 7 itself. So b will be equal to 1, and this part will be the polynomial with degree equal to 1. For example, suppose we have a reconciliation like this, and we have two base cases. So in this case, we can determine the characteristic equation for the homogeneous part. So in this case, like before, like last week, when we have Tn minus 3, Tn minus 1 equals to 0, then we can have a characteristic equation, r minus 3 equals to 0. So r will be equal to 3. So the general, so this is the solution we have. And from the term on the right hand side here, we know that b is equal to 4. From here, the polynomial is 2n plus 1, so that the degree is equal to 1. Hence, the characteristic equation we have is r minus b, which is 4, to d plus 1, which is 1 plus 1. So it is r minus 4 square. So here, r minus 3, we have it here, and r minus 4 square, we have it here. Okay, and from here, we get that the roots are equal to 3. It's supposed to be r1 equal to 3, and then r2 and r3 equals to 4. So you can see that 4 is a root for twice, right? So it is double root of 2. And here we apply the theorems we learned before to get the general solution. So we have C1 times 3 to n, because from here we know that, it's supposed to be R1 equal to 3. So we have the first solution to n, the second solution to n, and because it is doubled, so we have n times the second solution to n. Okay, so this is the general equation, and then we back to the base case to find the C1, C2, and C3. But we know that in the base case before, we have T0 and T1. But now we know that we have C1, C2, and C3. So we have three constants that we need to find the value. But we only have two base cases, so we need to find another one. So for three constants, we need three equations. For two constants, we need two. And for four constants, we need four equations. So here, because we have three, we need three equations, but we only have two. So we can find another one by using the initial reconciliation we had. So for n equal to 2, from the initial problem we have, we can know that T2 minus 3T1 is equal to 4 to 2 times 2 times 2 plus 1, like this. Just substitute 2 to n. Okay, and then from here, we can know that T2 is equal to T1 is 12 from the problem, the initial problem itself. So we can just solve this such that we can have T2. Now we already have three base cases, so we can use those three base cases to find C1, C2, and C3 by using substitution and elimination or whatever method you feel comfortable for it. But from there, we know that from n equals to 0, n equal to 1, n equal to 2, we already get the base cases. And then we know the general solution, so we substitute the value of n's to n, and get this such that from here we can use substitution elimination to get the value of C1, C2, and C3. And then you can substitute the constants obtained into the general solution. So we have this for the general solution. We just substitute C1, C2, and C3. So we get this as the final solution. Okay, so another example here, we have reconciliation. And from here, we can know that the homogeneous part. So for the homogeneous part, we will have Tn minus Tn minus 1 equals to 0. So the characteristic equation will be R minus 1 equals to 0. And then the non-homogeneous term, we have is n minus 1. So it is 1 to n times n minus 1, such that we have b is 1 from here. So we have b equals to 1, and the polynomial we have is n minus 1, such that d is the degree of the polynomial is 1. So from here, the characteristic equation we have will be r minus b, which is 1, to d plus 1 equals to 0, or we can write it as r minus 1 square equals to 0. So from the two, so the characteristic equation is r minus 1 from the homogeneous part times r minus 1 square from the non-homogeneous part equals to 0, or we can write it as r minus 1 cubic equals to 0. So we have r1, r2, and r3 equals to 0. And from that, we use the theorem we learned last week, that the general solution for Tn will be a coefficient C1 times the, oops, sorry, it's supposed to be 1, okay. So C1 times 1 to n plus n, because it is doubled, so we have n, and because it is tripled, so we have n square, okay. And because 1 to n here is always 1, so we can also write it as this. And now we have to find the value of C1, C2, and C3. So we need three equations. We need three base cases. So we know that T0 is equal to 0. And for T1, so from here, we know that Tn is equal to Tn minus 1 plus n minus 1. So T1 will be equals to T0 plus 1 minus 1. So we just substitute 1 to n here. So we have 1, 0, 1 here. 1, 0, and 1. Okay, where T0 is equals to 0. from here. So we will have another 0. And for T2, here it will be T1 plus 2 minus 1. So we just substitute 2 to n. So we have T1 here and 2 here. So from here, it is equal to T1 is 0 plus 2 minus 1, which is equal to 1. So we have T0 is 0, T1 is 0, and T2 is 1. By using the three base cases, we can have three equations from here by substituting n equal to 0, 1, and 2, and make it equal to the base cases we have. Okay, so these are what I demonstrate before. So you have three base cases now, 0, 0, and 1. And from here, you substitute for n equals to 0. From here, you will have C1. T0 will be equal to C1 plus 0 times C2 plus 0 times C3, and it must be equals to 0. So C1 will be equals to 0. And when n equals to 1, you will have T1 from here again equals to C1 C2 times 1 plus C3 times 1 square, and it must be equals to 0. So you will have C1 plus C2 plus C3 equals to 0. And because we already know that C1 is equal to 0, we will have C2 plus C3 equals to 0, or we can say that C3 is equal to minus C2. And when n equal to 2, you have T2 is equal to, substitute it to this again. So we have C1 times plus C2 times 2 plus C3 times 2 square, and it must be equals to 1. So you will have C1 plus 2C2 plus for C3 must be equal to 1. And from here, we know, and from here as well, we know it is 0. We can write it as minus for C2. So minus 2, C2 is equals to 1. So C2 is equal to minus a half. And from here, we know that C3 is, from here, we know that C3 will be a half. So from here, we can know that Tn is equal to Cn is 0, C2 is minus half, and C3 is a half. So this is the final answer. Okay, so from here, you can use substitution, elimination, and whatever basic operation you can do, and substitute the final solution for C1, C2, and C3 to the general solution, so you can have this as the final solution. For example, here we have two terms on the right-hand side. Again, when I say two terms, because the term we can have on the right-hand side will be in the form of Bn times a polynomial. But in this case, we have an addition, right? So we have two terms. This is the first one, and this is the second one. So in the first one, we have term n. The second one, we have the term 2 to n. So in this case, again, we have homogeneous part, Tn minus 2, Tn minus 1 equals to 0. So in this case, the characteristic equation will be R minus 2 equals to 0. Okay, and then the non-homogeneous part, is we have two terms. Okay, we have n to n. For n in the form of b to n pn, we have we can write it as 1 to n times n. So b is equal to 1 here, and then the polynomial itself is n, this part. So we will have the degree of the polynomial is 1. And from this, we can have 2 to n times 1. So b is equal to 2. And then pn is equal to 1. So the d is equal to 0. So the characteristic equation will be r minus b, which is 1 for the first term, to the degree plus 1. That is for the first term, and we multiply it with the second term. So for the second term, we have r minus b, which is 2 d plus 1 equals to 0. So the characteristic equation will be the homogeneous part, which is r minus 2, and the non-homogeneous part, which is this. Okay, so this is from here, and this is from here, and this is from here. Or we can also write it as r minus 2 square, r minus 1 square equals to 0. So we have r1 and r2 equals to 2, and r3 and r4 is equal to 1. So from here, the general solution will be Tn is equal to the first coefficient times the first solution to n plus second coefficient times the second solution. But because we use the same solution, we need to multiply it by n. And then we move to the second part. It is a new solution. And then the last part, it is the same solution. So we multiply it by n. Or we can write it as C1 times 2n plus C2 times n times 2n plus C3, because 1 to n is always equals to 1, and C4 times n, like this. And from here, we use the base case again. But we only have one base case here, and we have 4 coefficients, means we need to find 3 more base cases. So T1 is equal to 0. T2, from here, we know that Tn is equal to 2 Tn minus 1 plus n plus 2 to n. So T2 will be equal to 2 T1 plus 2 square. And it will be equal to 2 times 0 plus 6, which is equal to 6. And T3 will be equal to 2 T2 plus n, which is 3, plus 2 to n, which is 2 to 3. So in this case, we will have 2 times 6 plus 3 plus 8, which is 11. So here we have 23. And finally, T4, we will have 2 T3 plus n, which is 4, plus 2 to n, which is 2 to 4. And this is 2 times 23 plus 4 plus 16. no, sorry, 60, yeah, 16. 16, and this will be 66. So now we have general solution with four coefficients. We have four base cases. We can substitute n equals to 1, 2, 3, 4 to the general solution and find the C1, C2, C3, and also C4. Okay, so this is what we discussed before. So from here, we need to find C1, C2, and C3 by substituting n equals to 1, 2, 3, and 4 to the general solution and use the base cases we have. So we have this four equation and we can find C1, C2, C3, and C4. You can use substitution and also elimination, but me personally, I prefer using elementary basis operation. So I will use a matrix for presenting these four equations. So I can find C1, C2, C3, and C4 by using the basic uh, elementary basis operation. Maybe you should already learned this from the algebra or matrix classes. Okay. So from here we got C1, C2, C3, and C4, and we can substitute it to the general equation so we can get the final solution. Okay, for more practice, you can try this this linear recurrence relation to find the final solution for Tn. Okay, that's all I want to present to you. Thank you for watching, and please do the assignment I have on LMS. Thank you very much. Goodbye.